Hello, and welcome to the 5th episode of the MEER podcast, a show dedicated to science education, focusing on climate change, urban heat adaptation, and climate restoration using surface reflection technology. I'm Peter Dines, a director at MEER and the host of this podcast. Dr. Tao will be joining us once again to be our educator on this journey. Dr. Tao is the founder and director of MEER, which stands for Mirrors for Earth's Energy Rebalancing, an organization he set up to tackle the greatest threat that humanity has ever faced, namely climate change. Before setting up MEER, Dr. Tao was running a lab at Harvard's Rowland Institute. MEER is a non-profit organization focusing on surface SRM adaptation and mitigation research and also climate education, which this podcast is obviously part of. Over time, we will be discussing everything to do with climate reality, feasible mitigation, urban heat adaptation, the latest scientific papers, and what's going on with the MEER project on an ongoing basis. If you do have suggested topics that you wish us to cover, you can tweet us at MEERSRM on X, or alternatively contact us through our website, meer.org. Like I said, the organization is a non-profit and we are funded by individuals at this stage, so any donations are always welcome to further our research and humanitarian efforts. You can go to meer.org/donate to do so. In this episode, we hear about Dr. Tao's trip to Makeni, one of Sierra Leone's other main cities, where he intends to build water evaporation suppression experiments. And we also discuss the pressing topic of the loss of planetary albedo, or what some refer to as our Earthshine. Well, okay, let's get started. So how are things going on down there as usual? As I ask you every week. You just had a trip to Makeni, I think, as well, which is one of Sierra Leone's other major cities. Can you tell us what that was for and how you and the team were received?
We went down to EBK, University of Science and Technology in Makeni, to do a departmental visit, specifically the agricultural department. I had previously passed by the same institution as we were looking for collaborations around the country to see which campus, which area is more suitable for the different experiments we have going on. And the particular experiment involving testing water retention in artificial water reservoirs seemed particularly suitable for that location because they had a really nice campus with the land that's required for the experiment, which is also very nicely fenced off with 24-hour security. So that's pretty important because we do plan to put in a lot of valuable instrumentation, including a floating solar field and associated batteries, transformer, inverter, etc. So we, after looking at a few potential candidate sites and universities, we decided to propose a collaboration with them. And as part of the process to formalize the collaboration, we went there to give a formal visit, lecture, Q&A sessions, and also live demos for their faculty and staff last week. It was pretty well received. So the department obviously really wants us to participate. And some engineering department faculty also came, and their students also had a blast playing some of the plastic upcycling projects we had going on. Hands-on, they don't really have any experimental resource. All they do is theory, so getting a chance to use their hands to make something using some tools and instrumentation was quite interesting to them.
Yes.
So that's the purpose of the visit.
So that's a potential site then for doing the water evaporation experiments. Is that right?
Potential site for that, but also could be for agriculture. There's actually a couple more universities in the same city around that also have ongoing experiments on agriculture. And in general, I think Sierra Leone is pretty okay in terms of their research on agriculture. There's even like mulching for water retention going on in another city, Bo, in Jala University. There's also PhD research programs there, and they have produced decent research out of those sites. So we are more urgently looking for collaborators for doing water retention, but the agriculture application is also a part of the plan going forward.
Brilliant. And it was also Innovation Week there in Freetown last week, I think. So how did that go? And was there any feedback from that?
During that week, we also pitched and showcased our plastic upcycling project. I think in general, even in Sierra Leone, have this complexity bias, and they seem to be more impressed by things they don't fully understand. So surprisingly, but maybe not too surprisingly, a particular pitch about using aluminum as the source of energy for powering one-time use aluminum electrolyte battery for lighting purposes was picked as the winner of the pitch. And that's in spite of the fact that when you subject aluminum metal to this electrochemical oxidation process, you produce aluminum 3 ions, which are highly toxic and neurotoxins for both humans and aquatic ecosystems. So in countries such as Sierra Leone, where environmental protection laws and practices are not really in place, one can imagine that when such products get put into the market, it would result in immediate contamination of the soil and runoff into the ocean that would come back to the seafood that the local population depends on. So it's quite unfortunate that complexity bias is repeatedly exhibited in these pitch events.
Goodness.
Over here and also in the States, in Boston, same things go on. Complicated stuff such as decomposing plastic into constituent monomers, then performing the polymerization again, as opposed to direct upcycling use, as we're trying to do, get more attention. Because when the process is more complicated, there's potentially more process steps. There's more opportunities for collaboration with different funding agencies, different contractors. So it's all about maximizing profit potential instead of really address the root problem.
Yes, and again, it's they're not necessarily taking into consideration the energy requirements of the processes ongoing as well, which is something that we obviously factor into any of our projects. Yeah, I just wanted to get on to this week's main discussion then, which is around the subject of albedo and Earthshine. And, we've recently learned that the Earth's albedo or reflectivity is decreasing due to the melting polar regions and glaciers, etc. But why is it important that Earth's albedo remains constant at where it was at, around 30%?
Well, first of all, the multiple measurements so far has confirmed that, to the best of our knowledge, Earth albedo is around 30%, 0.3, meaning that about 30% of the photon energy in the spectral range between roughly 300 nanometers up to 2.5 micrometers or 2,500 nanometers are reflected when the light photon interacts with the Earth's atmosphere and lens surface. Of course, they change direction on the way out. And generally speaking, there's different ways to measure this parameter. You can do it more locally, such as by flying satellites that's close to the Earth's surface and scanning the surface several times a day. And you generally need multiple satellites to cover the whole surface area of the Earth, at roughly daily frequency. One can also do that indirectly, like by some rather ingenious methods. For example, setting up microscopes on the surface of the planet Earth, looking at our satellite, the moon, and comparing the light intensity coming from the bright side of the moon versus the dark side.
Yes.
Most people know that the bright side of the moon are due to light reflecting that from the sun directly. So the sunlight striking the lunar surface on the bright side, and then some of that gets sent in other directions, such as for the terrestrial observer. So the bright side of the moon is what we see as direct reflected light from the sun.
Yes.
But if you had a really good camera and a long integration time, it's actually possible to see the dark side of the moon. I think the intensity difference are different by like orders of magnitude, maybe 1,000, 10,000 times different. So you really need really highly sensitive instrumentation, probably cloudless nights, and absence of mechanical vibration in order to like the sufficient photon count to have a good signal to noise ratio. But nevertheless, it's possible to observe the dark side as well.
Yes.
Proper instrumentation. And I think even some like modern day cameras are getting pretty good. Some CCD cameras can even do that. Maybe not with the numerical accuracy that gets you plus minus 1% confidence interval for your error bar, but maybe just order of magnitude, factor of 10, factor of 2, let's say.
Yes.
Precision. So the different methods, they roughly agree that 30% of light gets reflected. And this number is important because it reflects the inverse of that, or the complement of that. So 1 minus 0.3 equals 0.7. That's the fraction of photon energy that's converted into heat at various locations and heights within the Earth's atmosphere, land surface, and in the ocean.
Mm-hmm.
So that's the total heat generation, the total heating power for planet Earth. Okay, so the reason why this albedo is important is because it more or less directly tells you the heating rate for the planet. And
Right.
when we're dealing with global warming, which is a thermal excess issue,
Yes.
one way to deal with that is to control the heating rate. If you turn down the heat, then we have less heat to worry about. Because right now the problem is directly caused by the heat unable to escape the planet due to greenhouse gases. But it has become increasingly clear that it's essentially impossible to deal with this issue by trying to reestablish the rate of heat escape. So
Yes.
our only option, regardless of how you do the intervention, is to reduce heat generation first. So that's why, from a global perspective, the Earthshine parameter, the Earth overall spherical albedo, called spherical because it's like they integrated over the whole sphere.
Yes.
Is one upper control knob of the process.
Yes. Yes. Understood. And yeah, very interesting. Now you're not going to see the dark side of the moon with a normal pair of binoculars, I'm guessing, but yeah, you need the right instrumentation. But yes, I understand you. So it's very important because that is telling us what the natural balance would be, and if we lose that natural balance, you're saying that's when the planet starts to warm.
At least on average, that's the expectation if we're looking at the global average. I think there's a lot of subtlety that the scientific community doesn't fully understand yet. It's ongoing field of research because I think most of the satellites are doing such measurements. For example, the Ceres satellite, the first one was launched in 1997. So it's like some 27 years since the first measurement. Well, subsequently, there were many other launches. So there's instruments, that's also supplying data to this, to make the series, what's called like the data product, which are not direct measurement, but more or less process secondary data based on a set of primary measurements that can also include ground-based stations to provide some constraints. So Ceres stands for Clouds and Earth Radiant Energy System.
Yes.
That's an acronym. Yeah.
In James Hansen's latest paper in Global Warming in the Pipeline, he talks about that Earth's energy imbalance. And so what is the Earth's energy imbalance then, I suppose, and what factors control that?
Well, roughly speaking, the sum between the net shortwave radiation balance and the long wave balance integrated over the whole globe gives you Earth energy imbalance, because ultimately energy in the form of, say heat or light, energy enter and leave the Earth via radiation of one sort or another. Basically, radiations are different parts of the electromagnetic spectrum. And it has to be the case because there's roughly no or very minimal exchange of materials between the planet and outer space. There's a certain leakage rate of hydrogen, but the rate is so slow, maybe order of like tons, kilotons, maybe a few tenths of kilotons per year. From a planetary perspective, it's a very small exchange of energy.
Yes.
So most energy happens within the electromagnetic spectrum. There's also some ion, cosmic rays, but those are, to the best of my understanding, very minimal compared to the power of the sun, which amounts to kilowatts per square meter. So a few ions passing per second through the same, say, 1 meter squared carry much less energy than that. Yes. So the dominant mode for exchanging energy between the planet and outer space is through radiation. And the dominant input mechanism is sunlight, and it's more or less directional. It's parallel to the line joining the sun and the Earth. But the exit for the energy from Earth can exit via more or less the whole surface, because the Earth itself, the surface and the clouds, can act as black body radiators to emit long wave radiation That's not visible to the eye, but interacts with greenhouse gases. Hence, they are able to perturb the exit side of the equation of the heat balance. So the Earth's energy imbalance then refers to the difference between how much net energy is coming in versus how much energy net is going out.
Yes.
So at the top of the atmosphere, you have what's coming in is the downwelling solar radiation from the sun. It's 1.3 kilowatts per meter squared. And then the Earth, due to Earthshine that we have talking about, sends about 30% of that upward. So the difference, the 70% is what's being absorbed, generated as heat into the planet.
Yes.
And then at every location, there's a different rate of IR radiation going out. You can conceptually integrate that over the whole sphere. That gives you a number, and then divide that back by the surface area of the planet, 5.1 times 10 to the 14 meters squared. That gives you then per meter squared the rate of energy departure.
Yes.
Then you make that sum or take that difference, whether you're keeping sign of the numbers with your directional convention or not. And then the difference is the net energy gain or loss by this black body of planet Earth. With total thermal energy content is what's interesting for you as a person, as a resident of this planet, as a plant, because that determines your environmental conditions.
Yes,
that includes temperature, radiation, and humidity.
Yes, and I think a lot of people are starting to realize that is a very important equation when you look at the heat waves ongoing in Asia and Mexico and other places. Indeed, some people misunderstand this as well in terms of if you have high albedo surfaces, why is it that does not then convert to heat? Because some people, actually in a conversation recently in India, there was some people that were actually thinking that if you had sunlight reflecting off the mirrors, it would still heat up. Where are they going wrong with that?
There's several potential sources of misunderstanding, and there's some validity to that concern as well. So sources of misunderstanding, first of all, is that people have generally do not distinguish between light and IR radiation or heat bleeding. Because when just experientially, when you go into the sun, say during a cold winter day, you can feel the warmth of the sun on your skin directly. So there's this intuition that sunlight equals heat, but that's not really true physically. You can feel the warmth from the sunlight striking your skin only because the photon has already converted partially into phonons or molecular vibrations in your skin.
Right.
So, and then we talk about heat being trapped. So if one has already made the equation between sunlight and heat, then of course, then sunlight will be trapped by greenhouse gases that interact with heat. But that's not the case. If we use high albedo surfaces or highly reflective surfaces that do not engage in photon to phonon conversion, then what's being sent off are incapable of interacting with greenhouse gases. So they more or less will go straight up through the atmosphere with a rather high probability of escape, depending on cloud conditions on clear days. In many locations, it's up to like 80%, 85%. Under very cloudy conditions, maybe like 40%, 30%. Yes. But nevertheless, a huge fraction makes its way out into space. It's as if, because it's at speed of light, it's as if it never was sent to Earth firstly. Or, roughly speaking, the sun has been virtually turned down, without actually doing anything to the sun from a Earth perspective. So what's partially, the twist is that not 100% can escape the atmosphere. There's never something as 100% purity in physics. It's just not possible. Yes. There's bound to be some probability of interaction, depending on, again, climatic and meteorological conditions. You have either really high absorption, maybe 80% absorption, up maybe went down to maybe 15% absorption on the way up.
Of course.
And it's also a complex function of travel initially when photon departs from the surface. When it's been sent horizontally across and probably hits your neighbor's house and it just bounces around and gets absorbed with 95% probability.
Yes.
But if it's to stand straight up on a clear sky day, 85%, 90% probability escape.
Right.
So this directional feature of reflection is also important. That's why we prioritize developing specular reflectors, more or less pointing towards zenith during solar noon, and optimizing in direction such that the product between, the inverse of the path of escape and the projected area of sunlight capture is a maximum.
So it's better than Lambertian reflection, you're saying?
Yeah, certainly it would be better than Lambertian reflectors from a global planetary cooling perspective, right? Because when you send a significant part of your light laterally at very shallow or low angles relative to the horizon, then they have a higher probability of being reabsorbed or rescattered by the atmosphere, gases, and clouds. That's why when you look at the horizon, it's generally more hazy than when you look up to the sky during slightly cloudy or hazy day. The cloud deck is just much thicker when you go across. Right?
Yes.
It could be like kilometers thick rather than maybe just 100 meters thick, depending on direction. So that's important.
So in terms
and I just want to close the thought. And because of this absorption in the atmosphere, a method such as what we're trying to test for mirror-based reflection or any other surface albedo enhancement is likely to heat up parts of the atmosphere. So, and the exact consequence of that really would require testing and modeling to fully understand. Right? You can imagine different scenarios. One scenario being that if you're able to partially heat some of the air, that would be equivalent to increasing the sensible heat that you're releasing into the atmosphere. And sensible heat, more or less the production of hot air on the ground, has been linked to the production of clouds. Because in order for clouds to form, what's necessary is the ability to transport moisture and condensation nuclei from the surface up to a level where conditions are such that you have condensed water as a more stable phase.
Mm-hmm.
And that's because temperature decreases with altitude. That's the lapse rate. So generally speaking, the ability to create uplift of air is beneficial for the formation of clouds. And perhaps under certain conditions, the reflection of light, heating air, overhead might perform that. On the other hand, it's also possible that you may have the light burning the clouds away because imagine you have some clouds forming and you suddenly now send light to the clouds and a portion of that will be absorbed. And that would more or less evaporate away the water droplets. So the exact balance between the two different mechanisms, that's something that requires experimentation aided by computational support. So it's not something that's easy to predict beforehand.
Yes, and it's certainly something that we are looking at and hoping to build a project around that science very, very soon. Also, in terms of the project, then, I mean, how effective would MEER prove to be as thermal mitigation when it comes to trying to balance the Earthshine once again? How effective could it be?
All right. So, I mean, there's the theoretical perspective, which, based on the discussion so far, suggests that a portion of the surface albedo enhancement would be translated into a spherical albedo enhancement for the planet. There could be, or I should say, most certainly would be some feedback parameter, which either enhances or degrades the local surface perspective, and as to whether the parameter is greater than one, less than one, that really requires additional science to be done. But one can imagine, like in the extreme case, let's say in the case of a historical precedent of snowball Earth, where all of the planet was covered by like white surface, basically ice and snow. In that state, that's a very stable state because the light, it doesn't really matter. The clouds really don't matter much anymore in
No.
that state, because even if they disappeared, the surface would still take care of the reflection. So in a sense, the worry about, say, a negative cloud feedback due to, say, surface albedo enhancement is alleviated, because even if locally there is a slight decrease in cloud cover, the light that were to come down, the additional light, still sees a higher albedo surface. So the fate of those photons is still being reflected upwards, just that the interception happens at a different level. Right? So if there's a negative feedback in certain situations, there's another positive feedback due to the sequence of events of how the photons travel. So generally speaking, then to first order, and the brightening of the surface would lead to an enhancement of Earthshine. From a resident of the planet perspective, the situation is a bit more complicated and actually more favorable, because from the Earthshine black box perspective, we are considering everything as just in this uniform, one-dimensional, well-mixed container.
Yeah.
That's decidedly not true for a planet that's composed of different continents that display a wide variety of local climatic conditions, and that has atmosphere and oceans with very height and altitude dependent conditions. And when the energy balance is perturbed at the surface, the initial perturbation is most certainly very large at surface level, at ground level. And as we mentioned before, we really expect to have a strong cooling of the surface and perhaps a somewhat warming of the atmosphere upward. But from the perspective of a plant or an animal seeking thermal shelter, undergoing thermal refugia, it doesn't really care that much if, say, the upper troposphere gets warmed up a little bit or not. What it cares more is between an ocean depth of minus 200 meters and a height of 20 meters above surface, what the micro climatic conditions there are, because that's the condition that's relevant for agriculture, for primary production, for forest regrowth, for fire season. So that again, there's the global perspective, and there's the local and height dependent perspectives that one needs to be concerned about.
Yes. And in terms of the breakdown coverage then for MEER, how do you equate that to urban areas and water bodies and agricultural settings? And what's the breakdown in terms of, because there's lots of people online or, speculating on how much would be needed here and there, and you'd have to cover the size of the United States and things like that. What is the breakdown in your mind for the figures that you've come up with?
Well, the breakdown is roughly 90% for agricultural water saving applications. And more and more, there's publications coming out suggesting that as you cover agricultural spaces, it's not like as if you're taking the land away from production.
No, that's not 90% of all agricultural spaces. You're saying that the project would be 90% agricultural, you're saying?
Yeah, I'm saying the total deployed sensor surface area, 90% of that would go into agriculture roughly.
Yes.
And that's only protecting, or we should say enhancing the productivity of 10% of existing agricultural land.
Right, 10%.
Yeah. And the 10% of deployed reflector surface area roughly would go into hydrology, into protecting freshwater evaporation.
Yes.
And then the remaining roughly 1% goes to protecting people's homes from overheating. And if we also include public spaces, if it really takes off, then we can aspire to maybe a couple percent of the total deployment, where people are highly concentrated in urban settings, in schools, in outdoor concert spaces, street markets, and hopefully for many of the existing awnings used for shading, your porch would be converted to MEER material without too much actual difference in the ease of using. It's completely compatible already with many of the structures.
Okay, and And in terms of the water side of things, what would you say to people that would say that the water bodies should be covered in PV panels instead of reflectors? And then do PV panels actually have a warming effect? There's a lot of PV panels going across inland water bodies currently, and everyone sees that as an easy fix and an easy access to energy, and a good place to place them.
It's not a bad idea in locations that are free from storms, but if your area, experience tornadoes or strong winds, I don't think it's a great idea. I think recently there's a huge reservoir in India that tested this technology, and based on reports and images that I could find, a lot of the PV panels were quite destroyed in the process of the loss. So it's not without risk for the investor to place them on water compared to more traditional ways to install them in fields with better anchoring and wind engineering design. Yeah, because the engineering of floating systems is certainly not as mature as those for land-bound installations. So that's something to be aware of. And secondly, there is no competition for space between PV and floating MEER because we have much larger total surface area freshwater reservoirs than needed by PV to supply most of our electrical energy. And of course, PV also has this infamous heating impact. It's converting a lot of the sunlight into sensible heat, raising temperature of the air, and that would negatively impact the living conditions of people living by lakes that previously provided for masking or hiding of the sensible heat because of the evaporation. But floating PV would also suppress evaporation to some degree, probably not as efficiently as floating MEERs because of the temperature difference. And that question to quantify the difference in water heating / warming between the two systems is something that we'll have to perform in Makeni hopefully coming year.
Yes, absolutely. Looking forward to seeing what the results are from that. If MEER was to be scaled to a certain level, could a certain amount of that cooling, if you'd start to build Earthshine back again, could that actually encourage natural albedo levels to reappear possibly if the heating was kind of slowed down or even reversed slightly?
No, definitely. And personally, I think that's the only feasible way to utilize nature-based solutions. If we look around the globe, the major carbon sinks like the Amazon forest and many drylands are becoming net carbon sources because drought conditions, and temperature conditions are such that photosynthesis doesn't happen sufficiently during the year to break even, the respiration loss and fire loss. So if at this point, this advanced into global warming, people are trying to, by brute force, plant trees, the end result would be wasting of effort because seedlings would hardly survive because even established trees are beginning to burn and fall ill to diseases due to the warming and drought. They become less resistant to these pathogens and also just physical degradation from flash drought and fire. So if nature solution were to play a role, the first condition is to stabilize local microenvironment. And there's no other way other than modifying the local energy balance can one achieve that. So if MEER, as hypothesized and also observed on the initial experiments in New Hampshire, is able to encourage the growth of plants, to encourage primary production by combination of lowering soil moisture and air temperature, then it should be doing the same thing when implemented nearby or within natural systems, like pine forests or other type of forests that are, or even over grasslands that are currently suffering from climate-induced erosion degradation. So I think the paper that we recently found that performed an experiment did an extrapolation to global. So they more or less essentially used a partially reflective film as potential replacement for greenhouse carbon that can turn down the temperature inside by selective IR radiation through the atmospheric transparency window.
Yes.
And they observed by lowering the air temperature inside greenhouses using surface cover, they were able to increase primary production. If those results were to translate to global grassland, they could achieve about 2 tons of carbon sequestration increase per year. And that's much superior to all of the nature-based solutions combined when they're globally scaled at this moment. So when you apply a approach such as MEER to actively directly cool, you get carbon sequestration benefits as a free co-benefit. You don't need to invest in teams to go plant trees and water them and keep track of them. No need. Let's just put MEER out there, give them to farmers so that they increase their production. And the cool air blowing from farms onto neighboring forests automatically encourages growth, of course, retains moistures for the forest, and everything ensues as a side benefit. So it's, I think, a very efficient method.
Yes, there's obviously there's a lot of co-benefits that are potentially come along with the project as well, which is what we're hopefully going to learn more about in our experiments over the next 12 to 18 months. And when you look at Almeria in southern Spain, where they've had that increase in Earthshine, if you want to call it, in a regional or local sense, what did we find from that indirect experiment?
So I think the result came as a surprise even for the people looking at it. Well, it's been a while since I looked at the numbers, but more or less the results were such that the air temperature within regions where greenhouse for agricultural purposes grew by roughly 50%. Air temperature in those regions dropped over the past 20 years by some degree or two, whereas the temperature outside of those regions increased by 2 to 3 degrees. So you have a differential of a couple of degrees to 3 degrees of cooling in absolute terms when albedo was increased for enhancing agriculture. And that region, in spite of its small size, apparently supplies a lot of fresh fruits and vegetables for the entire Europe. In many countries are importing from that small region.
Yes.
So it seems possible to create these artificial food gigafactories that operate very efficiently while locally providing a local cool spot. So reflective cool island.
Yes, there's a lot to learn from that indirect experiment as such. Just want to lastly ask you, because there was recently very heavy rain in Freetown, which actually came a bit earlier than was expected. But what was the result there in terms of the mirrored rooftops that had been covered in dust with the previous dust storms? What was the result of the heavy rains, and did we see a positive? I'm assuming we've seen a positive result in terms of albedo again.
Based on drone imaging, it seems like, and also both the visible and the iris signature, it seems like the reflectivity has been very well restored following the rainstorm. We have not done exact quantification analysis of the data, but just qualitatively, it seems like the rain does most of the job for cleaning. We haven't really done any artificial cleaning. Perhaps it's, I would imagine, maybe 70 to 80% back to the original state. There's probably some minor residual contamination of the surface, just based on visual inspection. But typically speaking, in many of our estimates for global impact, we don't assume that the film would be operated at starting pristine conditions.
Yes.
So it's normal to expect that in real world conditions, we never achieve 100% initial reflectivity. And that's also a reason why, in my mind, it doesn't really make sense to spend a lot of R&D money to chase the last few percent. So the difference between 95% reflectivity and 99% reflective is minimal. If by unavoidable urban brim deposition, you drop to 70% anyway, so the difference becomes the relative gain becomes minimal. for the last few percent material.
Yes, but you still need a material that's durable and lasts a certain length of time in the field, and obviously it has anti-soiling properties if possible.
Yes, at a certain point, the longevity of the film becomes a more important. I mean, certainly already is a more important parameter than the difference between reflectivity of 80%, 85%, and 95%. If the longevity is improved by a factor of 2, that's as if your reflectivity increased from 85% up to 130% from a cost analysis and the global scalability perspective. Because the parameter that we sometimes talk about, the cooling return on investment, how much energy you can remove, how much excess heat you can remove versus how much energy you invested to make the removal happen.
Mm-hmm.
That parameter, that efficiency figure doubles when you double the longevity of the film. But if you are focusing on getting the last, say, 5% of the reflectivity to get a better material, it's only a roughly 10% increase of your ROI. And as engineers, we like to double, triple, improve things by orders of magnitude rather than anything 5% academic.
Okay, well, listen, we'll leave it there. Thanks everybody for coming along as well and listening here. Great to see people. Some faces I know from Twitter and others I don't. But believe us when we say we are working around the clock, and there's no one works harder than Dr. Tao and his team in Africa. And and we look forward to having another conversation next month as well.
Thank you, Peter, for hosting.
So once again, we'll have to leave it there as we've come to the end of our time on this podcast. I want to thank Dr. Tao for his time and brilliant insights on these very important subjects that we all need to understand. Hopefully we've all learned something new today. We will hopefully be back again next month, delving deeper into the science and hearing updates on the project. Thanks to anyone who's tuned into the live stream and those listening to the recording. I hope you find the conversation useful and enlightening. Just a reminder, you can follow our developments at our website, MEER.org, or follow our X Twitter feed at MEERSRM. That's MEERSRM on X. And once again, MEER is a non-profit, and we do appreciate any donations that you can make towards our ongoing research and humanitarian efforts. To do so, please go to MEER.org/donate. Thanks again.